In the last part of this videos, we will talk about Ohm's law. This is a simple yet important physics law that describes basic properties of electric currents in conductors. It was found by a German physicist, Georg Simon Ohm, in the early 19th century. This law describes many properties of currents that we see in our everyday life. Let us first discuss the basic idea behind the Ohm's law. Suppose we take a piece of conducting material, shown by the red block here, and conduct a battery to the material. As before, blue balls indicate moving electrons. To create a current through the conductor, we need to apply a potential difference to the two ends of the conductor. So let's connect the battery to both ends and set the initial voltage of the battery to 0 volts. We will measure the current through the conductor using an ammeter that is connected into the circuit. Let us see how the current changes when we increase the electromotive force. If the electromotive force is 0, there is no current going through the conductor. The electrons are more or less at rest. As we increase the electromotive force, the electrons start moving, and generally the electrons move faster when the potential difference is large. We see that a larger potential difference across the conductor produces a stronger current. This is easy to understand. The stronger the battery pushes the electrons through the circuit, the faster they move and the stronger the current is. Whenever you get an electric element and wish to explore its electric properties, you can perform a very simple yet informative measurement. Connect a potential difference delta V to the terminals of the element and measure the current that goes through the element. Plot the dependence of I versus delta V for several values of delta V. The typical dependence that you will observe is shown in the graph. The larger delta V is, the stronger current you will observe. This dependence of I on delta V is of interest for many applications. It depends on both the design of the element, such as the shape of the element, as well as the properties of the material and physical parameters of the environment, such as temperature. Although the measurement of I versus delta V is very basic, it can tell a lot about properties of the electric element. Depending on the type of the element and its material, the I versus delta V can take many forms. In the simplest case, the dependence of I versus delta V is approximately linear for a wide range of delta V values. If the material obeys such linear dependence, it is called an ohmic material. Many materials, including metals, are ohmic materials. For ohmic materials, the dependence of I versus delta V is approximately constant. The inverse of the slope is called resistance R of the element. If we want to find the unknown resistance of some material, we can measure several I and delta V values and find R as delta V over I. We can also turn it around and find the current for given delta V and known R. If an element is made of an ohmic material, the current satisfies Ohm's law. I is equal to delta V over R. Here, R is the resistance constant associated with the element. R can be either measured or computing by knowing so-called resistivity parameter ρ of the material. If we take a conducting element such as a metallic wire, the resistance of the wire will generally depend both on the sizes of the wire and its material. For example, here is a cartoon of a piece of a wire and the expression for the resistance in terms of the length of the wire and the area of the cross-section of the wire. If we increase the length of the wire, the resistance generally goes up. There is more material for the electrons to penetrate, hence the resistance is also larger. If we decrease the length, the resistance gets smaller. If we increase the area, there is more material in the transverse direction for electrons to pass through. Think about a wider pool for water to flow through. The electrons can more easily avoid impurities in the material. So when we increase the area, the resistance generally goes down. If we decrease the area, the resistance generally goes up. Finally, some materials are more conducive to the flow of the electrons than the other, and this is described by the parameter called resistivity ρ. Inside the material, the resistance occurs because of constant collisions of electrons with the atoms of the material. The stronger the atoms move, the larger the resistance will be. This implies that both resistance and resistivity depend on the temperature. When the heat motion is relatively small, resistance can be low. On the other hand, as the temperature increases, the resistance is expected to go up. Rapid moving atoms create more obstacles for the electrons flowing through the conductor. To remind you, heat motion is the chaotic motion of atoms of the lattice that vibrate violently in no particular direction. There is a substantial energy stored in the energy of moving atoms. On the other hand, electrons follow the general direction of the current. In the shown picture, they move from left to right. Because of the heat motion of atoms, resistivity of the material goes up as the temperature increases. Here is a typical chart showing dependence of resistivity on temperature. In many interesting cases, the dependence of resistivity on temperature is approximately linear in a range of temperatures. In this case, we can approximate the observed resistivity dependence by a linear equation. If we know the value of resistivity ρ0 at some temperature T0 and the slope of the resistivity dependence ρ0 alpha, then the equation for resistance at any temperature T is expressed in terms of the resistivity ρ0 at temperature T0 according to the equation shown below. For many ohmic materials, resistivity coefficients ρ0 and alpha are tabulated in references that you can readily find on the internet. It is important to include the temperature dependence when you evaluate parameters of typical electric elements. Resistivity can change dramatically when the element heats up in the process of its running. Temperature dependence of resistivity is practically important. When the current travels through the conductor, it heats up the conductor. The electrons bounce into atoms of the metallic lattice and transfer their kinetic energy. As a result, the kinetic energy of the electrons is dissipated as heat. The temperature of the conductor increases, hence its resistivity. The power with which the energy of the electric current is dissipated in the form of heat is described by Joule's law. Joule's law states that the power of heating P is given by the product of I and delta V. Using Ohm's law, we can also write the heating power as I squared times R or delta V squared divided by R. By energy conservation, the energy lost from the circuit in the form of heat must be equal to the energy supplied into the circuit by the electromotive force during the same time t. The formula for the released heat energy, E, is equal to I times delta V times t. It must be equal to the work of the energy W during the same time. The conservation of energy can often be used if you know the powers of various elements in the circuit or the energy supplied into the circuit during given time. To summarize, resistance, resistivity, and conductivity are property of ohmic materials that relate the current through the material to the applied voltage. It is important to distinguish between resistance and resistivity. R, the resistance, is the property of the whole electric element. It describes the resistance to let the current I pass through this element for given delta V. On the other hand, ρ and sigma are the properties of the material. Conductivity sigma, ability of the material to let the current pass, and the resistivity are related as ρ equal to 1 over sigma. In this slide, I collected all equations related to Ohm's law and the current through ohmic materials. You can apply these equations when computing for most typical conductors. There are many other types of materials whose conductivity properties are very different from those of ohmic conductors. For example, dielectrics have low conductivity, which means that I for a given delta V is essentially zero, For semiconductors, the conductivity can vary from low to high, and I will be variant dependent on what delta V and environmental conditions are. Superconductors have essentially infinite conductivity. I through the superconductors is very large for each given delta V. An interesting dependence of I on delta V is observed in many insulators. In general, insulators have no freely moving charges inside. In a typical insulator, such as rubber, plastics, or air, both positive and negative charges are bound inside the molecules. They cannot freely move inside the dielectric. Therefore, if we apply some potential difference delta V, I is pretty much equal to 0 for a large range of delta V, unless delta V gets very large. If delta V gets large, it polarizes molecules and pulls positive and negative charges apart. If delta V across the insulator increases, it creates a stronger electric field that pulls charges apart. Eventually, if this force is strong enough, it breaks down the molecules. Suddenly we start having plenty of positive and negative charges flowing through the dielectric. We can get a very large electric current with the same value of delta V. We get a phenomenon called a breakdown, when the dielectric suddenly becomes a good conductor. The lightning is an example of the breakdown when the air becomes a conductor. We suddenly see a current that goes from the thunderstorm cloud into the earth with a very spectacular effect. Another interesting class of materials are called superconductors. In these materials, resistance falls essentially to 0 when temperature goes below a certain critical temperature Tc. On the right-hand side, we see the graph of the resistance versus the temperature of the superconducting material. If the temperature is high enough, in this case it is above 4 Kelvin, the resistance follows the regular dependence on the temperature. It is definitely non-zero. However, if the temperature goes below Tc, suddenly the resistance of the material becomes exactly 0. In this case, inside a current that will exist inside the material for indefinitely long time. The current is created by the electrons that move through the material without losing their energy to the heat and motion of atoms. Therefore, since there is no loss of energy, the electrons can move inside the superconductor forever. The value of Tc is sensitive to a number of parameters, including chemical composition, pressure, and molecular structure. As I said, once a current is set up in a superconductor, it persists without any applied voltage, since R is equal to 0. Superconductivity is a fascinating property. It allows one to create electric currents that encounter no resistance. For example, electric energy can be transferred in superconductors to large distances without any loss. As we will learn later, electric currents create magnetic fields around them. So superconductors are employed to build powerful electromagnets installed in MRI units at hospitals or advanced science facilities such as the Large Hadron Collider. On the downside, applicability of superconducting devices is limited by the requirement of very low temperatures of order a few Kelvin that are needed to reach the superconductivity regime. Development of the materials that become superconducting at even higher temperatures of order 100 or 200 Kelvin is an important direction in physics of condensed matter.